Thank you very much. It's a pleasure to be here. So first of all, this is based on joint work with Ivan Perez, which of course means that Ivan did all the hard work, and I am here to take some of the credit for his hard work, okay? So Ivan did his PhD with me a few years back in Nottingham on FRP and related things, and we still do a bit of FRP in Nottingham. Of course, Ivan also founded a company called Kira Studios that you might have heard of. In the previous talk, Christina talked about Kira and what they do there. And now he has moved to NASA as a researcher. And he still does some of these things. So much of what we're going to talk about today are actually also relevant to Ivan in his everyday work at NASA. Okay. So, this is mainly about testing, okay? So thorough testing is never easy, we know this, but of course some systems are perhaps harder to test than others. And your mileage might vary what you consider hard or easy, but I think that games is an example of things that are quite hard to test quite often, or reactive systems in general, right? Now, why is this so? Well, we have reasons like difficulty of specifying adequate input for adequate test coverage. I mean, if you think about the game, you have someone playing this game. How can we ensure that this game has been played in all possible ways to reveal all the bugs? And the truth is that in real life, game companies tend not to do that. They just release the game and then hope that they will get some bug reports back, and that then somehow will enable them to figure out what went wrong. Okay, so it's very hard to test games thoroughly. Another is lack of reproducibility. Here's one example of that. This illustrates a force field-based graph layout algorithm. The idea is that these nodes, they repel each other unless they're connected by a little line, in which case there's an attraction there. And then you just sort of let the kind of physical simulation loose, and you sort of see how these networks converge, and that's then the graph layout. Now the thing is that even if you have exactly the same initial state, the end result might differ quite dramatically depending on exactly when you sample these systems to carry out these computations, right? So same initial conditions, but actually very different end results, even though you had what looks like a quite pure way of describing this system. So to phrase that a different way, we have interaction with the changing outside world at times that are sometimes difficult to control exactly, and that makes for difficult testing. Okay. Of course, these are all quite general challenges. There is nothing particularly functional about them, nor does functional programming particularly help addressing these challenges as such, right? We can write individual components in our systems in a pure way, and they will still be subject to these difficulties. However, what I will try to argue in this talk is that if we think functionally about the whole system, okay, if we aim for some kind of referential transparency at a system level, then we can mitigate these difficulties. And in particular, then we can use techniques that are proved effective in a pure setting, also at this system level setting. So that's the message of this talk, okay? And I will illustrate using arrow-wise FRP, and then in particular Yampa, that you might have heard of. Come back to that in a little bit. And show that using tools that Ivan, mainly, through all his hard work, developed, we can get things like 100% reproducibility. We can use ideas like quick check and property-based testing to increase test coverage. We can do things like record and replay debugging, but in a way which is very high level, relies very little on the underlying systems, so we get cross-platform and we don't need to assume much about underlying systems. In fact, all his tool needs is a couple of sockets, and that's about it, which is pretty impressive, really. We'll come back to that later. Okay. So, now I expect that many of you will know FRP quite well. So apologies to you guys, but nevertheless, for the benefit of those who might not know what FRP is about, I'm going to give you a rough idea at least, or cover the key ideas, in order to, so that you can appreciate the point of structuring your systems using in this particular way. So here's the key idea of FRP. Don't program your systems one time step at a time, but instead try to describe everything as a whole, as an evolving whole, program with time-varying values. And of course, we are quite used to do this in other fields, like in physics. If you want to describe, say, a ball falling towards the floor, you set up a couple of equations, a couple of differential equations or integral equations in this case. And they say, well, okay, if we have a ball and it starts at some initial height over the floor, y0, and we have this ball at it has some initial velocity, then when time starts going forward, what's going to happen? Well, this velocity is going to increase as the ball accelerates under the influence of gravity. And we can describe that just by integrating this minus 9.81, which is the acceleration due to gravity. And we get then the velocity at every point in time. And then we integrate the velocity and we add the initial position over the floor. And then we have the position of the ball at all points in time. Okay. So that's a very natural way of describing a system like this. Okay. So shouldn't we program our systems in the same way then? And FRP allows it to do that. Okay. So what is it? Well, it's one way of viewing FRP is that it combines the simplicity of synchronous data flow programming. It's been around for a long time, but it's mainly discrete, with the flexibility, discrete time, with the flexibility and abstraction power of high-order functional programming. Okay. So it's synchronous programming and a bit more, and in terms of features, yes, it's synchronous, so things happen in lockstep in this system, so time progresses at the same rate across the system, if you like. We have these first-class temporal abstractions. Also in the flavors of FRP I'm going to consider here, we have hybrid notion of time, so we can have both continuous time, which is the basis, and then we can have a discrete time on top of that, so things can happen at specific points in time as well. Well, I will not talk so much about that in this particular talk. Okay. And then we have dynamic system structure. And by that I mean that we can sort of have configurations of our system that evolve over time as well at specific points in time. I'll show a picture of that in just a little bit. Okay. And anyway, if you have all these features, this turns out to be a good conceptual fit for many applications, including games and physical simulations, and many more. We have done, for example, lots of, or at least a fair few, musical applications using this. There have been virtual reality simulations and lots of things. Okay, so I mentioned Jampa. So Jampa is the flavor of FRP I will be using in this talk. It's a FRP implementation embedded in Haskell, structured on these three key notions: signals or time-varying values, functions on these signals, and they are pure functions, okay, mapping signals to signals. And then we have this notion of switching, which is temporal composition of signal functions, and this is what allowed the system to evolve structurally over time. And I will not talk so much about that in this particular talk. But it's there, and it leads you to this kind of programming model. You can view these arrows here are essentially illustrates how signals flow through the system. The boxes are signal functions and processing these signals, driving a new signal from an input signal, or two, or three, whatever you might have. And then the cloud there in the middle illustrates that this system, how things are wired together, can change at different points in time. So the system has a dynamic structure. And this is one thing which sets this FRP, or Jampa in particular, then, systems apart from, say, synchronous data flow programming, where things tend to have a specific fixed structure. Jampa now is almost 20 years old. There are lots of different FRP systems out there. They all have different pros and cons. Jampa is certainly not without its flaws. And indeed, if you heard the previous talk, Christina said that Kera Studios, Ivan's company, are now moving away from Jampa towards a more general thing based on something called monadic stream functions, which I will briefly say something about later, time permitting. But anyway, I think it has become a bit of a reference implementation over the years, and lots of people have used it for lots of different things, including for games. And so here you see a game called Frag, that's now quite old. I think it goes back to 2005-ish something, which is a first-person shooter game implemented partly in FRP. Okay? I think the game logic is in FRP, whereas the physical engine is not. Okay? And then you have a couple of Kira Studio games over there, and Puzzle and Landabot, and I think these are essentially in FRP and Jampa and other pure functional programming stuff. Okay. So to give you a little bit more on what goes on inside a Jampa system, so we had this notion of signal functions then, and how can you think about signal functions? Well, the intuition is this. We have time, and as I said, time is fundamentally, we want to at least pretend when we write our programs that time is continuous. I'll come back to that point in a little bit as well. So this is to a first approximation. We have continuous time. And then we can think of our signals as functions, pure functions, mapping time to some value. So if you have a signal of type A, that's really a time-varying value of type A then. So now we can have signals x and y of some type T1 and type T2. And then we can write a signal function. And in general, signal functions, you can think of like this, that they are roughly pure functions, taking a signal of one type to a signal of a different type. So in particular then, the f up there in that picture, if x is a signal of type T1 and y is a signal of type T2, then f will be a signal function mapping signals of type T1 to signals of type T2. And that's mostly it, except that of course we also have to make sure that we respect causality here. So future input obviously can't, input can't obviously, the output can't depend on future input, right? If it could, I would be a very rich person by now, okay? Because then I could predict the stock market or whatever, but I can't, because it's impossible. Right, so trying to think about things like this, but you also need to keep in mind that, of course, this has to be realizable in the real world, so we have causality in addition. And there's a couple of simple signal functions. We have the identity signal function, unsurprisingly, which essentially does nothing. Just whatever comes in goes out. We have the constant signal function, has a constant b as its output. And here's a slightly more interesting one then. The integral signal function, which says that at every point in time, the output is the integral of all of the input up until that point in time. And now when we build systems, what do? Well, we just take these signal functions and plug them together, okay, using combinators. So here is one combinator, serial composition, which just is function composition then, because we're talking about pure functions here on signals. And we have a combinator, this is triple arrow, that captures that particular idea, and it's just reversed function composition. And of course, if you know about arrows, you will see this is the arrows composition, serial composition operator. And in fact, Jampa is structured using arrows, so there's a few more combinators to glue signal functions together in various ways. But surprisingly, you don't need that many combinators to be able to describe whatever network you like. There is only a handful of them, thanks to the arrows formalism. Anyway, the key point here is that what we now have is a pure system-level description, okay? And that's what's going to help us to test this in a more principled way. And before I move on to testing, I just want to say a few words about the arrow notation. So combinators are quite nice in many ways, but when you have a fair few signal functions around and you want to glue them together, it becomes a bit cumbersome to do it using just combinators. So we have this arrow notation that essentially allows us to take a network of signal functions in this case, more generally a network of boxes with inputs and outputs. We can name the inputs and outputs, and once we have named them, we can just have a textual description that says how are these things wired together. So in this case, we can see that the box F there, it needs to get X as an input, as well as the fedback V as an input. And here you can see how we feed X and V into F, producing a U. And you see then how the U up there is sent to both G and H. You can see here we have U going into G and U going into H there. And that rec keyword here is what enables us to feed back the v from here to up there. So there's a bit more to this arrow notation for Haskell, but as far as Jampa is concerned, there is really nothing more than just a way of textually describing a network. We don't use the more advanced feature of the arrow notation. Okay, and that's certainly all you need to know for this talk. Of course, this is only syntactic sugar, just like the notation in Haskell in general. Everything is translated into the underlying combinator syntax. And it's quite common to mix both this notation and the combinator notation. That turns out to be the most pragmatic way of writing this kind of code. So let's return to the falling ball example. Okay, so here's the falling ball again. Here are the equations again. I've simplified a little bit. I now assume that the initial velocity is 0. And then you can see the code here in using arrow notation in Jampa that basically transliterates these equations into executable, something that we can run. Okay. And yes, there's a bit of syntactic noise here, but I hope you agree that what's written here is indeed very close to what's up here. Okay. So we have this integral of minus 9.121 giving us a v, and then we integrate that v, and we add on the initial position, and we have our y, and that's the roll output from this falling ball. Quite nice and declarative, I think. And again, this is a description of a whole system then, in a pure way. That should make it easy to test if you do it this way. Okay, so before I move on, any questions at this point? Is everything clear so far? Sort of, you know what FRP now roughly is? Yes? Good. So then let's move on to how can we test something like this. I said before that now the benefit of having a pure functional description of the system as a whole is that we now can employ techniques that are proved particularly effective in a pure functional setting for testing our reactive systems as well. And in particular, we want to use property-based testing and quick check to do this. But to use something like quick check, which has proved to be quick check is not limited to a pure setting. You can use quick check for all kinds of things. But I think it's fair to say they've been proved particularly successfully in a pure setting. It's particularly easy to use in a pure setting. And now we have a pure setting. Except then that in our case, we have these time-varying values. So if you want to talk about properties of time-varying values, we need to turn to temporal logic to express those properties. Let me say a few things about temporal logic, or more specifically about the version of temporal logic we have inside our testing framework for FRP. Okay, so we take a bit of a pragmatic approach to temporal logic, or an FRP-ish approach. So we view temporal propositions as time-varying booleans to make a blend with the rest of the FRP thinking. Okay. Having done that, we can now define the semantics of a temporal logic in a fairly straightforward way. So for example, if we have a logical condition of AND, we can just define that point-wise over time, over our temporal propositions, or time-varying booleans. Of course, we need some modalities, okay, to talk about what happens, for example, in the future. So here is the always modality. It takes a temporal proposition, and it says that this temporal proposition should be true from now on forever. Okay. We have eventually, which says that, well, this temporal proposition will become true at some point. Okay. And then we have one which is more specific to our framework. We call it imminently. And it says something is not true right now, but will be true very, very, very soon indeed. Okay. So it's the right limit coming from above towards the current point in time of that given temporal proposition. So this is sort of the ideal semantics for that temporal logic. Okay. but we're interested in testing. So how can we test things like this? And the answer is, well, you can't really, because if we have continuous time, there is no way we can sort of test every point in continuous time. It just doesn't even make sense to even say that. Also, we obviously can't talk about all the points into the future. Again, things have to be causal one way or another. So we couldn't test that, or at least not in my lifetime or your lifetime or the lifetime of the universe. Okay. So we need to make some refinements here. We need to sort of take a bit of a step back in order to make this testable. So the first thing we do is that now we are going to, when it comes to testing, we are going to discretize time. And of course, the pointer is that while we are allowed to, for the most part, write our FRP programs, our YAMPA programs, pretending time is continuous, at some point we need to realize when we execute it, that's not going to be true. We are going to discretize time and then run the system at a number of discrete points in time and see how it evolves at this discrete point in time. So obviously then what we do is that we now implicitly define the time domain for our logic to coincide with this discrete point in time of a particular run. Okay. We simply don't know what happens in between these discrete points in time. Still, I would argue that it's still very helpful to be able, when you set your predicates, when you set your properties of your system, to think about what should be true in general as if time was continuous. And then not worry too much about this discretization that has to happen when we run the system. And then we get two flavors of our logic. One that we can use after the fact, once a run has terminated, to check properties, because that means that we now have a limited time, and we can then talk about what happened in this limited time span. Okay. So when we say for all, always, for example, it means, yeah, this is going to be true always up until the end of a particular run. And eventually means, yes, we expect to see something before the system terminates. Actually, no, it doesn't, but that's a different point. Okay, but we also have this other variation, because sometimes it's useful to be able to say, to state things that you expect to hold in your system and then be told whenever that's not true immediately. In particular, this helps us to run systems for as long as we like and find bugs before they have terminated. So we have a different version of this logic, which is sort of backwards looking or history-based, which we can use to put assertions into our code. And then whenever an assertion is violated, that's caught immediately, and we can then start debugging from that particular point. So these are the compromises we have to make this logic testable. Okay, and here you see just what the after-the-fact temporal logic looks like concretely as a Haskell data type. So you can see, to begin with, we have so now before we had temporal propositions, and now we have temporal predicates on the input signal to the system, or to a part of the system. And then we can take any signal function on that input signal that's outputs a Boolean, and turn that into temporal predicate. It's unsurprising. And then we have the logical connectives and the modalities, like always, eventually, imminently, and also something called after. We expect them to hold after some particular point, after some particular amount of time. Okay, so let's state some properties about our falling ball, unless there are some questions about the temporal logic here. It's all clear to people. Yeah, good. So if I have a ball and I drop it, and we are in a world where we have sort of the ball falling towards the floor under the influence of normal gravity, we expect that the ball will fall towards the floor. In particular, then, if I drop it from here, I never ever expect it to be up higher than from where I dropped it. So we can state that to say that, okay, if we drop the ball from height y0, then the output, the position, as it varies over time, well, so this actually says that this is just the predicate saying that this is true whenever the position is below the initial or not higher than the initial position. Okay, that's what all this says. And then we can use that to say, well, I expect that this ball will never ever be higher up than it started, by saying always ball fell over. Okay. But of course, we expect something more than that. It's not just that the ball will never ever be higher up than it initially was. We also think that it always will keep falling. It will never sort of fall here and then go up a little bit and then go down again if gravity is normal gravity. Okay? So we can refine this to say that, well, actually, what I'm expecting is that the derivative of the position of the falling ball, its velocity, is always going to be negative. It's always going to fall towards the floor at all points in time. Okay? So always derivative of the position should be less than 0. And the only caveat here is that, of course, when we start, the derivative is not well defined there. So I need to say that, well, okay, at all points except for the first one. So imminently, I expect the derivative to be negative. And of course, you could go on and say something about that the velocity is also always going to increase if this is just falling under the influence of normal gravity. But instead, let's look at something else, namely this. We might want to make the ball bounce once it hits the floor. Okay? And if we do, it's natural to say that for a bouncing ball, I expect it to always be above the floor, regardless of what happens. And that was stated down here. For a bouncing ball, I always expect the position to be greater or equal to 0. Okay. Is this a good property? Do you expect it to hold? Yeah?
Wouldn't there always be a problem?
Sorry?
Wouldn't it always be a problem?
Yeah. Ideally, it's a fine property, but in practice, as we'll see, there are some caveats. So yes, you've probably seen this kind of issues before. Anyway, so let's keep that falling ball property, the bouncing ball property in mind, and let's see what happens. So now we can start doing some quick checking. Now that we have a language to talk about properties over time-varying values. And this then helps us to systematically increase the test coverage by random testing. Okay? We have ways of supporting this. There are some generators that are a bit experimental that generates inputs. And in particular, then we can talk about, remember now, we are in a discrete time setting, so we need to talk about the sampling times, for example. And we have ways of saying that we want different sampling strategies, whether sampling should be very sort of precise and regular, or whether the sampling times should jitter a little bit, and if so, how much, and so on and so forth. Okay. Also, which is quite cool, and we'll come back to that as well, is that we can have recorded inputs from, say, a game that has been run live, and then up to close where there was a problem or where we expect there might be a problem. And then we can extend such an input in random ways, because it can be quite hard to cold start a system like this, and in effect impossible to then find the way through the game states, for example, to where there's something interesting happens. So then why not simply record actual input to a point where we sort of know the game is now in an interesting state, and then we can explore randomly what happens from there. Okay. So if we now use this property, test ball over floor from before, on a simple stream with an even, where we sort of just pick the time deltas between sample from a uniform distribution. And then we run our ball over floor on this, okay? And then we say that for all inputs, we generate this randomly, we expect this ball over floor property to hold. And what happens? Well, we may get a little shock because our property fails straight away. And now looking at this, we say, well, of course it fails. Because here the time differences between these samples, they are huge. So the first one is 4.43 seconds. The next one is 1.27 seconds. And then we have 3.00 seconds. So of course, the ball had plenty of time to fall through the floor before we looked at it again. Obviously, it failed. Okay? So let's be more clever. Let's generate a more sensible input with much more dense sampling and see what happens. So we do. Okay. So now we have more like 60 frames per second here. But to our dismay, this test still fails. Okay, well, still not a good property. And then we have to scratch our head, and then we are forced to realize that, well, okay, we can think in an idealist way only so far, right? So in this case, we're now forced to say that, okay, while always above the floor holds ideally, in either case here, because when we actually run the system, it's not ideal. So either we have to admit that our implementation is a bit too naive, so maybe we need to do some implementation to make it closer to what ideally would happen. And there are ways of doing that. There are ways of detecting collisions, say, between the ball and the floor quite precisely, or as precisely as is needed. So maybe we should go down that route. Or we should simply say, okay, I understand that this is going to be a bit coarse, but I'm happy to provide some slack in my properties. So maybe it's okay if the ball is a little bit below the floor, just not too much. And we can, of course, refine our property to capture that if we want to. Okay. I think the key point was that through stating this property, we now are forced to think more carefully about the system and think, okay, what do we actually want to be true for this system? What is an acceptable system behavior? And also that, of course, depends on what you're trying to achieve. At this point, I would like to make a call for properties, okay, on behalf of Ivan in particular. So I'll show you the URL in a bit, so you can actually download and use this stuff. And we would be very interested to know what kind of properties you would like to test in your systems, because this is nice, but it's still a bit prototypical, and having some real input, feedback as to what kind of property matters to you guys will be extremely helpful. So here it is. If you're interested, you can go to this URL and get the debugger. And there are two parts to it. There is a way of instrumenting applications to allow record replay debugging and so on. And of course also all these libraries for the temporal logic and assertions. And there is a GUI, okay? And these communicate via sockets, so minimal system assumptions, and enable to do things like remote debugging, for example. So you can record your playing session. Yeah, this is fine. Along with, say, the time you found the bug, and then you can send this back to the developers, and they can then replay this exactly. So in fact, I can demonstrate this. I have a little video. Just shows the record and replay. So here we go. This is the Kera Studios HaskellX game, I think. Yes. And first, Ivan starts his game, telling it to record the input to a file. And here we go. It's a breakout-like game. And then, having recorded to new trace.ytr, we can now replay this. And you will see exactly the same thing happen. And I mean exactly the same thing happen as it did before. Okay? So this is 100% reproduction. And we can do it again if you want to. Or 3 times or 4 times, or until you find the bug. Okay, Let me go back to the presentation here. So developers, they can now, they can replay traces, they can move to the time of a bug, they can move backwards and forwards, and while they do this, the game will stay in sync. So you can actually see time going back and forwards in your game. It's pretty cool. You can add assertions to sort of try to pinpoint places where there might be a problem more precisely, and more. The interface looks like this. And in particular, here we have a illustration of the input stream, and this red bit here indicates that this is where some kind of assertion or some assertion in the game has been violated. So we could then move time forward to that particular point and see what was going on there, for example. And if we had troubles understanding why our ball over floor property wasn't true, we can animate this ball over floor, and then we can record a trace of it and then see what happens. So here is a trace. It's a recording of that ball over the floor. That square there is a poor rendering of a ball over floor. Okay, and here we can then see that indeed it falls down under the floor, and then probably should be clear to us, okay, yes, of course it did fall under the floor. I should have known, okay? And the nice thing then is that we can now do this back and forth in our debugger, and we can explore the trace, we can insert assertions at other points and see, try to understand better why it went wrong. This has been used to find real bugs in games, for example, in HaskellX. So it was the case in HaskellX. Yeah, okay, I should say, okay, so what are good properties for games like this? Well, varies, of course, but a reasonable property for a game like HaskellX is that the ball should always remain within the screen. It's a variation of the ball above the floor property. Okay, we expect that to hold. And as it turned out, it didn't. It was possible to hit the ball with this paddle by a sort of quick flick of the wrist in such a way that the ball got a very high speed indeed, and then it just tunneled out of the game. Okay, and not obvious that was the case, because I had to play for quite a bit before something like that happens. Okay, but it did happen. And then thanks to record and replay, it was possible to pinpoint the reason for this, and then the solution was to artificially cap the speed of the ball, so that within the reasonable frame rate, the ball then would always stay inside the screen. Okay, so that's the end of the main presentation. I would just like to say a few words about monadic stream functions. So they are like signal functions, but parameterized on a monad here. And that gives a lot more flexibility. In particular, if that happens to be the IO monad, then each individual signal function cannot talk to the outside world. Okay? It makes it harder to reason about the system, of course, but it also gives a lot more flexibility. So for example, using this, monadic stream functions, it's possible to do things like hardware in the loop testing. Okay? So we can have a system of signal functions wired together, but some of these signal functions, or at least one of them, can actually be real hardware. Okay? And then we can now test a system with hardware in the loop in the ways you have seen like this. Okay. It's also possible to do things like fault injection and fault tolerance. Okay? So we can wire things together, and then we can, from the outside, say, okay, now I want this, that, and that component to fail. Now what happens? Okay. And then when you see that your system falls over abysmally, you can say, okay, now let's construct our system in a way which is fault tolerant, introduce, say, some kind of redundancy and things, duplication or computation nodes or whatever, and then see what happens. Okay. And then thanks to randomized testing, you can sort of see how much more robust your system becomes in the face of various fault injection scenarios and stuff like that. And this kind of things is stuff that NASA is very interested in, so that's part of what Ivan is working on these days. Okay, that was the end of my talk. There are some stuff you can read if you're interested. There's a paper from ICFP from a couple of years ago. And we have a new extended version of that paper that's currently undergoing reviewing, but we hope it will be accepted at some point fairly soon. So I think what you have seen in this talk is essentially all covered in the ICFP paper. Some of the newer things like the hardware-in-the-loop testing and fault injection and so on, they are covered in this new paper. Okay, thank you very much.
Great stuff. Okay, got a couple of minutes for questions. No? Aha.
You talked about generalization of this technique, and then in the last slide, I think you showed a monadic functional stream. So
yes.
What sort of constraint does it have on the M?
Well, as far as the implementation is concerned, there are no constraints. You can plug in whatever M you like. That makes sense. That's a slightly different question. We don't impose anything. It's up to you to make sure it makes some kind of sense.
So if you were a physicist and if you wanted to simulate a ball, you would almost certainly use an integration algorithm with an adaptive time step.
Yes.
Like RK45 is the simplest one. But doing this in Yamper, I think that has some relevance to your bouncing ball as well, because you're hitting you'd want to control the time step when you're hitting the floor. Now, that seems to be a problem for the Yamper framework, because you'd want the time step to be under the control of a combinator that's deep inside your network.
Yeah.
So has anyone done any work on this?
So you're absolutely right. A physicist who really wants to simulate falling balls or anything more sophisticated would probably not want to use Yamper. Okay? It's not really intended for a real physical simulation. It's good for things like games. It's good for things like illustrating the idea of a falling ball. But if you really want to truly do modeling and simulation, you shouldn't really use Yamper. That said, I think people have thought a little bit about making Yamper a bit more sophisticated in terms of the kind of numerical reliability or the kind of methods we use under the hood. There hasn't been too much progress on Yamper as such, because it's being reactive and so on, you're a bit constrained in what you can do. However, there is another line of work called functional hybrid modeling, where we do take the proper simulation aspect much more seriously, and it's in part inspired by functional reactive programming. I don't know if that answered your question or not, but you're right. As a physics simulator, Yamper is most of the time too naive. Yes.
Any more? Okay, well, Henrik, thank you very much. Big round of applause, please.
Thank you.